This is our program, which is a standard Connect 4 game with a 7x6 board, win conditions being 4 in a diagonal, horizontal, or vertical position. When a win condition is reached, we return a winning score for the max player and the opposite for the min player. There are over 4 trillion unique states for Connect 4. We use Alpha Beta Pruning to reduce the game state tree. Since we can't evaluate down to the terminal nodes, we created a fitness function to determine the value of the non-terminal nodes, limiting the search depth to 13. The program tests these possible win conditions. 3 in a row followed by a blank, 2 in a row, a blank space followed by 1 in a row, 1 in a row, a blank space followed by 2 in a row, also any orientations of these configurations. In addition, the program checks the trap conditions. Trap conditions are when there are at least 2 possible win positions available for the next move. The trap and win conditions are used to calculate a score. Instead of storing the game board in an array, we use a technique which is commonly used for chess solving program called bitboards. Bitboards is a data structure used to store the positions of the pieces. It is a 64-bit long int. A bitboard is needed for both max and min players. Using a bitboard greatly speeds up the processing of win and fitness values for each board. The logic for testing is also significantly simpler as well compared to an array-based implementation. Take the bitboard, bitwise shift a copy of it to the right, and run the AND operation. If any position in the boards overlap, the resulting AND operation will produce a 1 at that position, meaning a horizontal 2 in a row exists. This happens simultaneously for every position on the board. To check for vertical 2 in a row on our 2x2 board, we need a bitwise shift to the right 3 times. It will differ for major and minor diagonal as well. Since our implementation, we can traverse the entire game tree until terminal nodes, we have used a few methods to speed up the search. Alpha Beta Pruning, limiting the depth of search, and using hash tables to store previous values. In order to store the best move values in a hash table, we have to figure out a way to hash the board states to a unique key. The method that we use to do this is called XOR-based key generation, and it is commonly used in chess. For each space on the board, the red and yellow pieces will have a unique random number associated to it. For every piece on a specific board state, all the numbers associated to the red and yellow pieces on the board are XORed together. This will result in a unique key for every possible combination of boards with very minimal collisions. One final method of reducing the game state tree that we have used is reordering the traversal of the game tree. Through experimentation and research, we have noticed that more often than not, these center columns are resulting in a better score. Alpha Beta Pruning will always prune the most nodes when the best nodes are evaluated first. We try to estimate the score of all neighbors of a node in order to determine the best order of the traversal. This turned out not to be so feasible, at least in our implementation, because the cost of this implementation of ordering costed much more time than was gained. So we opted to take a much simpler approach, which was to evaluate the center columns first, then move outwards. This approach worked really well, as it reduced the time of computation by a rough estimate of 35%. We used these following methods: Alpha Beta Pruning, hash tables using XOR-based keys, depth limiting to 13, center out traversal reordering, and quicker logic using bitboards, which allow us to heavily reduce the time of computation versus the standard minimax algorithm and create a decent AI that plays Connect 4.